Welcome back, everyone, to lecture 10, where we'll be talking about additional rules for exponents. For and a lot of in this one, as opposed to the first basic rules for exponents, we're talking about numbers, um, or like exponents, but with the same bases and how you would combine them like that. Because in the other video, in the last lecture, lecture 9, about the basic rules for exponents, we were dealing with different bases and their exponents. And when I say base, I just mean the number that's being raised to raised to a power, like a number that has an exponent attached to it. We're dealing with different bases, so we didn't really have to worry about combining them. In this video, we're going to talk about combining them, and there's a few different ways to do that. When you're multiplying numbers with exponents that are of the same base, we add the exponents together. So just in general, for any number, say x, say you had like x to the 6th times x to the 4th. Notice how we have the same base because we're talking about x in both cases. So it's the same base. And like I said before, base is just the number being raised to a power, or the number that has an exponent attached to it. If you're multiplying two of the same base with different exponents, and you just add the exponents together. So this, to combine it, you would say it's x to the 10th. So you just add it together, and that works the same even if you had like a negative exponent, like x to the negative 2nd times x sixth to the x to the 6th. You add them together, so you have negative 2 plus 6, which is x to the positive 4th. So that's how you work with multiplying the same base with different exponents. You just add the exponents together. Excuse me. Okay, the next topic that we could run into when working with the same base is dividing numbers, the same numbers with different exponents, like dividing like bases with unlike exponents. In that case, you subtract the exponents. So say you had like y to the 8th divided by y to the 5th. In this case, since y and y are the same, they're the same base, but with different exponents, you would subtract in this case, and you'd end up with y to the 8 minus 5. So it'd be y to the 3rd power as your result. And that's how you deal with dividing numbers or dividing the same base with a different exponent. You just subtract the exponents. The last, I guess, topic of this video, aside from what we learned last time, the only thing that only other new thing that we're really covering is negative exponents. In this case, when we have a negative exponent, to make it positive, you flip it over the line of division. And what I mean by that is, for example, if you have like z to the negative z to the negative 6th. To make this exponent positive, we know every fraction, or like every whole number, or every number can be written as a fraction over 1. So the line of division that I'm talking about is just the fraction line. So to make this exponent positive, it would become 1 over z to the positive 6th. Likewise, if you had, say, like 1 over a cubed, or I'm sorry, 1 over a to the negative 3rd power, to make this positive, you'd once again flip this over the line of division to make the exponent positive, so you'd have a positive 3 over 1. And that's how you deal with negative exponents if they ask you to fix them and make them not negative anymore. You just flip them over the division line, and that's all that you have to do. Okay, so with that information in mind, and with the information in mind from the last lecture, let's get to it, and we can go through these pretty simply. You know, like, exponent rules behave pretty nicely. You can use them in a lot of different ways. Okay, so a lot of these questions are true or false. And like I've consistently said, when they're asking a true or false question, you're always going to want to do it yourself to evaluate what's going on. So what we have is 6 to the 6th over 6 cubed. which comes down to the dividing like bases with unlike exponents, which we talked about. All we have to do is subtract. So in the first one, 6 to the 6th divided by 6 cubed is going to be 6 to the 6 minus 3, which is 6 cubed. And then like we talked about in the last lecture, if you're evaluating this, this is 6 times 6 times 6, which is, sorry, we're going to go up here this time. It's 36 times 6, which you can do the multiplication on your own. I have full faith in you. Indeed turns out to be 216. So this is, in fact, true. Okay. In number 2, we have b to the 51st power divided by b to the 17th power equals b cubed, true or false. Okay, so for this one, we do the same thing. We have a similar base. We have b and b, both raised to different powers. So this actually would then turn into b to the 51 minus 17. Ooh, I'm sorry, excuse me, I just yawned a little bit. It's been a long day over here. Which is b to the 34th power. I can back up. Oh, okay, I guess it's not gonna work with me. Oh, for goodness sake. There we go, that's better. B to the 34th power, so this one's false. What they tried to do here is trick you and think, oh, you're dividing, so divide 51 and 7, or divide 51 by 17 in the exponent so you get to the 3rd power. That's, a common trick they'll try to pull. Don't fall for it. Know when you have a situation like this, you have to subtract the exponents. Okay, moving along. What we have for number 3, remember how we talked about last time, whenever you raise something to the 0th power, it's always going to equal 1, no matter what expression it is, because you'd distribute this 0 exponent in and multiply it to the other one, so you'd end up with r to the 0 power over s squared minus 1, the quantity to the 0 power, s squared minus 1 quantity raised to the 0 power. In either case, anything raised to the 0 power is 1, so this is false, because this should equal 1, but they're saying it's equal to 0, which is false. Just remember, anything at all raised to the 0 power is 1. Just pay attention to where the 0 exponent is. Since it's outside this entire quantity, you're raising that entire quantity to the 0th power, so it would equal 1. If that 0 exponent only applied to the numerator or denominator individually, only the numerator or denominator would be equal to 1, not the whole expression. But since that exponent is applied to the entire expression, the whole expression will then be canceled and equal to 1. Okay, number 4, aside from true or false, we actually get to evaluate something on our own. We have v to the 25th over v to the 47th power. So since we're dividing in this case with the same base with different exponents, we're going to subtract. So we're going to end up with v to the 25th minus 47th, which is going to leave us with v to the negative 22nd power. If your professor is okay with you leaving it this way, then cool, but we can use the negative exponents rule, which is where we would change that v to the negative 22nd over and move it over the division line to make it positive. So we can think about this as v to the negative 22nd over 1. And then we'd move this over the division line into the denominator to make it the exponent positive again. So we'd end up with 1 over v to the positive 22nd power. And that would be our final, I guess, proper answer, so to speak. Okay, moving along again, we have a very similar situation. It's just this time, instead of a variable, it's going to be similar to the first question where we're dealing with numbers. Just make sure that the base, if they're giving you an actual number, are the same, and we're dealing with 11s both times, so it works out. Like we can apply the rules. In this case, we're dividing So we're going to have 11 to the 15th minus 17th power, which is 11 to the negative second power. Same thing here, and especially in this case, you're going to want to make that exponent positive so you can evaluate this because they gave you a number that you can evaluate. So we're going to have 1 over 11 squared, or to the positive 2 power. Sorry, that was kind of messy. Let me fix that. Let me rewrite this because that was just not good and very illegible. Okay, so we're going to have 1 over 11 squared. And we know 11 squared is 121, or 11 times 11 is 121. So we have 1 over 121 as our final answer. Okay, so in this next one, we can do one of two things. We can either distribute the -2 to both of the exponents individually first, and then multiply those two numbers together at the end, or you can evaluate what's in parentheses to the best of your ability first, and then apply that outside exponent last. It's up to you either way, as long as you do it the right way, but it's kind of just depends on the situation. If you have two numbers that are of the same base, that you're multiplying together in those parentheses, we might want to, consider doing that first, just for the sake of, making it easier overall. Okay, so in this case here, if you notice, 8 is 2 cubed. So what we can do to maybe make this a little bit easier is, change that 8 up, knowing that it's equal to 2 cubed. So what we could have then is 2 cubed to the -1st power times 2 to the -3rd, all raised to the -2nd power. Well, 2 cubed to the -1, or remember from last time, if you have two exponents next to each other connected by only parentheses, you multiply them together. So we're going to have 2 to the -3rd times 2 to the -3rd raised to the -2nd power. And 2 to the -3rd times 2 to the -3rd, it's two of the same base being multiplied together with exponents. So we add the exponents together. So this is going to end up being 2 to the -6th raised to the -2nd power. Now we're just down to, we have two exponents connected by parentheses, so we multiply them together. -6 times -2 is +12. So our final answer is going to be 2 to the +12th power, which is quite a large number. You're welcome to plug that in and evaluate it for yourself, but you should be able to leave it just as 2 to the +12th power, which, in case you're wondering, is 4,096, which you can plug into a calculator for that, because expecting you to do it otherwise would be a little ridiculous. It's a very large number from twos. So you can leave it in either of these forms, to the 12th or 4,096. They're the same thing there. Okay. If you wanted to consider this a different way, the other way, hold on one second, let me find space. I'll do this one again at the bottom, or over off to the side, just to demonstrate that there is in fact another way to do it. There's almost always multiple ways to do what you want. It's just up to you how you want to think about it. So if we had that 8 to the -1st times 2 to the -3rd raised to the -2nd power, what we could do instead, if you so chose, since if you wanted to consider these, different bases and not modify the 8 to match the 2, if you didn't realize that, and or if you chose not to, you could distribute and multiply this -2 exponent to both of these separately, and then multiply last. So what you'd have is 8 to the -1st raised to the -2nd power times 2 to the -3rd raised to the -2nd power, and then evaluate both of these separately and then multiply them together at the very end. So you'd end up with 8 squared times 2 to the positive 6th, which then you'd have 64 times times 64 as well, which equals 4,096. Either way works. That's another way to think about it. If they were looking for, I guess, like, or if your answer choices were limited to being in a base raised to an exponent, like the 2 to the 12th representation, you'd have to notice that 8 is in fact 2 cubed, and then you could evaluate it further. But if you're strictly evaluating it numerically and you just wanted, like, the numerical full answer of 4,096, either way I'll get you to the same thing, either method. You just have to make sure you do both of them consistently like that. For example, like if you were talking about number 7, I would probably choose to do it this way, because you're dealing with things of 2 different bases that you have no chance of combining, because 5 and 9 like don't share a common base, like, because 8 can be broken down into 2s, but 9 can't be broken down into 5s, so you'd kind of be at a loss there. Okay, so in this case, what we would do is you can distribute and multiply this -2 to the other exponents of the other bases separately. So what you'd end up with is -5. Oh, I'm sorry, it shouldn't be -5. I'm getting ahead of myself here. So what you end up with is 5 to the -2nd power raised to the -2nd power times 9 to the 1st power raised to the -2nd power. And for the sake of not having to go below or above, I'm going to erase this because we have used it already. Use this rule. I feel like it's we've gone through that one. Okay, so in this case, when the exponents are connected just by parentheses, you multiply them together. So we'd have 5 to the -2 times -2. So we'd have 5 to the positive 4th. And then we have 9 to the 1st times -2. So that's 9 to the -2. And then to simplify this even further, we could, we'd have 5 to the 4th times 1/9 squared, which then you'd have 5 to the 4th, multiplying the fractions together, 5 to the 4th over 9 squared, which is 625 over 81. Simply just got those, the first, the top number, the numerator number, by just plugging it into a calculator. 5 to the 5 caret to the 4th power. And then, the other one, 9 squared, I just knew, or, you could also plug that one into a calculator. Those don't really divide nicely or anything like that, so you can just leave them how that are, leave it how it is. It's an improper fraction, 625 over 81, or 5 to the 4th over 9 squared. Either one works. This is the final answer you would get down to. You'd end up with some, long decimal number. It doesn't divide nicely. So you can just leave it as is, and move on with your life. Go out and see the world. Okay, so moving on, we're getting this one's a little bit longer of a lecture because there's a lot of different applications you can do with this, and a lot of different combinations they can throw at you. So we want to make sure we cover as much as we can. Okay, so for the next one, in this case, since we have variables here, I would follow this method outlined over here for this one, just because we have different bases that we can't combine. Like 4, m, and n are all different numbers. We can't combine them anyway, with the other exponent rules we talked about up there. So you would distribute this -3 and multiply it to all of the other exponents, including the one on the 4. Don't forget about that too. Like when there's variables and a number, you have to apply that exponent to all of them to get the right answer. So we'd have essentially 4 to the first power, because you can always assume that a number can be raised to the first power, to the negative, oh my goodness, these threes are not having it today, negative third, times m to the negative ninth to the negative third times n to the negative fifth to the negative third. So once again, now that we have it in this form, we just multiply all the exponents together, or the two exponents together on all of the different bases. 4 to the first times negative 3, or 4, like in the exponent, 1 times negative 3 is negative 3. So we have 4. That is not a 3. To the negative third power, negative 9 times negative 3 is positive 27. So we have m to the positive 27th power. And then negative 5 times negative 3 is positive 15. So we have times n to the positive 15th. We don't have to fix the two variables because they have positive exponents. We don't have to move that at all. The 4 to the negative third power, we can write as 1 over 4 cubed, and we know 4 cubed is 64. So this whole thing becomes m to the 27th, n to the 15th over 64 in the denominator. So that would be our final answer. Okay, moving along more. It's some more of the same, except we have two different expressions that are separately raised to their own exponents, two different groups. Goodness gracious. Okay, so what we do in this situation is very similar to what we did up one, in number 8, just twice essentially. So the process is going to be to apply this negative 2 into this set of parentheses to both of the exponents, and then to apply this 3 into this set of parentheses with both of the exponents, and then combine the new exponents of the similar bases, which is a lot of words to spit out all at once. So let me go through it with you so you see what I'm talking about. So this negative 2 gets applied to the 7 to the negative second and g to the 7th. So we'd have, as one quantity, we'd have 7 to the negative second times to the negative second times g to the 7th to the negative second first that we have to evaluate, then times 7 to the negative second cubed times g to the 4th cubed. Oop, goodness gracious, cubed. So in terms of the exponents for 7, we have negative 2 times negative 2, which is positive 4. So this is, in one set of parentheses, 7 to the 4th. I swear the stylus is not vibing today at all. It just keeps wanting to do its own thing, and I'm just not having it. So we have 7 to the positive 4th. G, 7 times negative 2 is negative 14. And then times 7, negative 2 times 3 is negative 6. We have 7 to the negative 6th. G, 4 times 3 is 12. So G to the 12th power. So what we do now is realize, okay, we have, let me get a different color for these. Okay, so we have a 7 and a 7. And then we also have a G and a G. So we have different bases here, but we can combine the ones that are the same. So in that regard, we can rewrite this as 7 to, and when you multiply these, or when you multiply two bases with different exponents, you add the exponents together. So we have 7 to the 4 plus negative 6th, and then we multiply that back to G times negative 14 plus 12, which then 4 plus negative 6 is negative 2. So we have 7 to the negative second, and then negative 14 plus 12 is also negative 2, so we have G to the negative second. in both, and this is all, all over 1. Since both of these have negative exponents, we can flip them both over the line of division to make them positive again. So this would end up being 1 over 7 squared g squared, or if you want to simplify even more, 1 over 49 g. And this would be your final answer. Okay. The only thing you can really do in number 10, since you're dealing with 4 completely different bases, is fix the negative exponents, and that's all we're going to do. So what we realize we need to fix here is all the negative ones. So this r to the negative third needs to get moved over the line of division. The s over negative fifth needs to get moved over the line of division, and then u to the negative 12th needs to get moved up over the line of division. So when we do all of that, think about what we have in the numerator. The r and the s are both moving to the denominator, and the u is moving to the numerator. So we're going to end up with u to the positive 12th in the numerator only, and then t to the 7th doesn't move, but r and s do. So we're going to have r cubed s to the positive 5th, t to the 7th, all in the denominator. And that would be all that we have to do. And that's as much as we can simplify that. You just are you're making the negative exponents positive instead, because that's what's conventional. And that's all that you have to do for that problem. For this one, once again, you can do it one of 2 ways, and I'll do both because it works the same exact way either way you do it. You know what to use? I guess we use black. We haven't done that in a while. Okay. So, method number 1. Sorry, I completely forgot that I actually have to write the problem down. That might be helpful. I wasn't stupid sometimes. It would help. Okay, so what we can do first, since we're dealing with things that have similar, the same bases in there, but, and that's all raised to the negative 2nd power, is we can evaluate that expression in parentheses as much as possible and then apply that negative 2nd exponent to everything afterwards. So that's what we're going to do first. So what we're first going to do, we have the 5 to the negative 7th, b to the negative 8th, over 5, to the negative 9th, b to the negative 4th. Okay, all raised to the negative 2nd power. So you can choose to make all of these negative exponents positive if you want to first. You don't really have to. The same rules apply when you're dividing them, even if the exponents are negative. You just consider that you have negative numbers. So for evaluating the 5s, we have 5 to the negative 7th over 5 to the negative 9th. Well, since we're dividing the same base with different exponents, we subtract the exponents. So we're going to end up with 5 to the negative 7th minus the negative 9th. Oh my goodness. Can we work with me, please? Okay, cool. So we have 5 to the negative 7th minus the negative 9th. But when you have minus a negative, it's the same thing as plus a positive from a way throwback in our lectures. So we have 5 to the negative 7th plus 9, which is positive 5 squared. That would remain. When you evaluate the b's, you'd have b to the negative 8th over b to the negative 4th. And then that would, when you do that, you subtract the exponents. You have negative 8th minus a negative 4th, which, again, since you have minus and negative, it's the same thing as plus positive. So b to the negative 8th plus 4, which is b to the negative 4th overall. So then when you consider that new expression that you have, we have now, in parentheses, 5 squared b to the negative 4th, all raised to the negative 2nd power. Now, since we don't have any more similar bases to combine, we can distribute this -2 in here, this -2 exponent to the other exponents. So you're left with 5 squared to the -2 times b -4th to the -2, which then, +2 times -2 gives you -4. So this is 5 to the -4th times b to the +8th, because -4 times -2 is +8. So then we'd have, if you wanted to make this final exponent positive, we'd have b to the 8th over 5 to the 4th, which is b to the 8th over 625. Either of these should, this should be an 8. Either of these forms should be acceptable. If you wanted, a specifically numeric answer, when you have like a number raised to a power, you can just evaluate it using a calculator. 5 to the 4th is 625. B to the 8th we can't do anything else with because it's a variable. We don't really know what else they would want us to do with it. Okay, so now, okay, I guess it's gonna keep scrolling, which is not what I wanted. Okay. Okay, there we go. Now, if we consider a second method, method number 2 perhaps, there's a different way you can do this to get to the same outcome. It really just, depends on what you like. It is completely up to you, because it will give you the same answer either way. We're just going to black this off so we can use method number 2. Okay. So method number 2, where we have the same 5 to the -7, b to the -8th over 5 to the -9th, b to the -4th, all raised to the -2nd power. One thing you can do, or a different way you can do this, is you can first distribute this -2 exponent to everything in here, to all the other exponents in here, in the numerator and denominator, and essentially kind of like work in reverse from what we did last time, where you apply this outside exponent to everything first and then work backwards. And it's worth noting here too that you can only apply this exponent to everything if it's being multiplied, like if the terms are being multiplied together. Because if you notice how up here there's s² -1 in the denominator, you'd have to apply that 0 exponent to this whole expression, the s² -1. So when it's subtracted by, or when it's with subtraction in the middle, or addition or subtraction in the middle, so this would be r to the 7th to the 0 power over this entire quantity s² -1 raised to the 0 power. Just so we're clear there, that's why I can distribute it to everything down here, and how I've distributed it to everything before is because all of these terms are being multiplied. They're combined by multiplication, not by addition or subtraction. So I can apply that exponent to all of them separately like that. Just, it's worth noting so that you don't, make that mistake. Okay, so following, I guess, the same thing we did on here, 5 to the -7th times -2, -7 times -2 is +14. So in the numerator so far we have 5 to the +14th power. And then -8 times -2 is +16. So we have b to the 16th. And then in the denominator, -9 times -2 is +18. And then -4 times -2 is +8. Okay, following the same thing for these different bases now. 5 to the 14th over 5 to the 18th. When you subtract those, 14 minus 18 is -4, so you're left with 5 to the -4th. When you subtract the exponents for the b's, you have 16 minus 8, which is once again just 8. And then same thing as before, The b to the eighth can stay in the numerator. This 5 to the negative fourth can go to the denominator to become 5 to the positive 4. And then if you simplified it even further and evaluated that number, it'd be b to the eighth over 625. Same exact answer as before, two different methods. Totally up to you which way you want to go, whatever makes the most sense. The first method number one, is probably leaves the least room for confusion, I guess, because you don't have to apply that outside exponent to everything at first. Maybe leaves less room for error. However, you can do it either way. It's totally up to you, however you want to do it. Just make sure too, if you're applying an outside exponent from outside parentheses to an entire expression that's, with multiplication and division and everything, be careful what you're applying it to, because if you're applying it to a situation like this, all of these things in the numerator, the term in the numerator and the term in the denominator are each combined by multiplication. What I mean is that, like, this 5 to the negative 7th is being multiplied to b to the negative 8th, just like this 5 to the negative 9th is being multiplied to b to the negative 4th. So they're being multiplied together in each case. So you can apply this exponent to everything separately. Whereas, like I kind of highlighted up here, this s squared minus 1 in the denominator, those two terms are being I guess combined by addition / subtraction, in this case subtraction. So you'd have to apply that outside exponent of 0 to the entire expression rather than just each term. So that's just something worth noting. It might, it'll help you out. I hope this was helpful, and I will talk to you in the next lecture. Thank you. That's the wrong button.